For 90 years, we measured the universe expanding at one speed. We calculated how fast galaxies fly apart, how quickly space stretches when the Big Bang occurred. The number is called the Hubble constant, and it is the most important measurement in cosmology. It tells us the age of everything, the size of everything, the fate of everything. We thought we knew it. We were wrong. The universe is not expanding at the rate we calculated. Different measurements give different answers, and the disagreement is getting worse, not better. This is not a small error. This is a crisis that threatens to destroy our understanding of cosmic history. If you want to see how the most important number in astronomy fell apart, stay with us. This is the story of the Hubble tension, and it changes everything we thought we knew about the cosmos. Open your cosmology textbook. Find the Hubble constant, the number that describes how fast the universe expands. For decades, we argued about whether it was 50 or 100 kilometers per second per megaparsec. Teams fought over measurements, careers were built and destroyed defending different values. Then technology improved, measurements converged. By the year 2000, we thought we had it. 70 kilometers per second per megaparsec, give or take a few percent. Case closed, problem solved. Except it was not solved at all. It was about to explode into the biggest crisis in modern cosmology. The Hubble constant works like this. Measure how fast a galaxy moves away from us. Measure how far away it is. Divide velocity by distance. That gives you the expansion rate. Do this for many galaxies at different distances. The pattern should be consistent. Farther galaxies should move faster in direct proportion to their distance. This is Hubble's law, discovered in 1929, the foundation of observational cosmology. Simple in principle, nightmarishly difficult in practice. Because measuring cosmic distances is hard, incredibly hard, and every error in distance measurement shows up in the Hubble constant. The distance ladder is how we measure the universe. Start with nearby stars. Use parallax, simple geometry. Watch them shift position as Earth orbits the Sun. This works for a few thousand light years, no more. Beyond that, you need standard candles, objects with known brightness. Measure how bright they appear. Calculate how far away they must be. Cepheid variable stars are the first rung beyond parallax. These stars pulse with periods related to their luminosity. Measure the period, know the brightness, calculate the distance. Henrietta Swan-Leavitt discovered this relationship in 1912, revolutionizing astronomy. For a century, Cepheids were the gold standard for measuring nearby galaxies. Type Ia supernovae are the next rung. These exploding stars reach consistent peak brightness, bright enough to see across billions of light years. Use Cepheids to calibrate nearby supernovae distances. Then use supernovae to measure distances to far galaxies where Cepheids are too faint to see. Each rung depends on the one before. Each calibration carries uncertainty forward. Errors accumulate. Small mistakes at nearby distances become huge errors at cosmic scales. This is the fundamental problem with the distance ladder. You are building a tower to measure the sky, and every brick you add makes the structure more unstable. The local measurement of the Hubble constant uses this distance ladder. The Hubble Space Telescope observed Cepheids in nearby galaxies, measuring distances with extraordinary precision. Then astronomers found type Ia supernovae in those same galaxies, calibrating the supernova brightness. Finally, they observed supernovae in distant galaxies, calculating recession velocities and distances. The result, 73 kilometers per second per megaparsec, with an uncertainty of just 1%. This is a triumph of observational astronomy. Decades of work, thousands of measurements, sophisticated analysis. The team, led by Adam Rees, won a Nobel Prize for related work. Their measurement should be correct. It is built on solid physics, careful observations, rigorous statistics. The cosmic microwave background gives a completely different answer. This radiation, the afterglow of the Big Bang, fills the universe. The Planck satellite mapped it with exquisite precision, measuring temperature fluctuations to parts per million. These fluctuations encode information about the early universe, its density, composition, expansion rate. Feed the measurements into cosmological models. Calculate forward 13.8 billion years. The model predicts what the Hubble constant should be today. The answer, 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. This measurement is completely independent of the distance ladder. It uses different physics, different data, different analysis. It should agree with the local measurement. It does not. The disagreement is 6 kilometers per second per megaparsec, 6 times larger than the combined uncertainties. 9% does not sound like much. In everyday life, being 9% wrong is close enough. But in science, when two measurements disagree by multiple standard deviations, something is seriously wrong. At first, astronomers assumed systematic errors. Maybe the Cepheid calibration was off. Maybe dust obscured distant supernovae, making them appear fainter and therefore farther than they really were. Maybe the cosmic microwave background analysis had subtle mistakes. Teams checked everything: dust corrections, metallicity effects, selection biases, statistical methods. Every systematic error they found made the problem smaller by a fraction of a percent. The core disagreement remained. The two measurements kept giving different answers. The Hubble tension is what astronomers call this discrepancy. Tension is a polite word. Crisis is more accurate. One of these measurements must be wrong, or both are wrong, or our understanding of the universe is fundamentally flawed. There are no good options. The local measurement uses straightforward observations of stars and supernovae. The cosmic microwave background uses our best model of cosmic evolution. Both have been checked and rechecked. Both appear solid. Yet they disagree. This is not how science is supposed to work. When careful measurements contradict each other, usually one is obviously flawed. Not this time. Both measurements are excellent. Both teams are competent. Both results are published in top journals. And they are irreconcilably different. New measurements made it worse. As instruments improved and uncertainties shrank, the disagreement became more pronounced, more undeniable. The Hubble constant should have converged. Different teams should have gotten the same answer within error bars. Instead, the local measurements cluster around 73. The early universe measurements cluster around 67, and the gap refuses to close. It is getting wider. This is alarming. It means the discrepancy is real, not a fluke, not measurement error, but something fundamental about the universe that we do not understand. The calculation continues. The measurements improve. The crisis deepens. And somewhere, in some dataset not yet collected, some theory not yet proposed, some observation not yet made, the answer is waiting. The answer that will resolve the Hubble tension, explain the sigma-8 discrepancy, solve the lithium problem, all of it. The answer that will transform cosmology from a field in crisis to a field reborn. That answer is coming. The only question is when. Meanwhile, the universe keeps revealing surprises. The more we observe, the stranger it becomes. Black holes are more common than we thought. Stellar mass black holes number in the hundreds of millions in our galaxy alone. We only detect them when they accrete matter, flaring in X-rays, or when they merge, producing gravitational waves. Most are invisible, dark against the darkness of space. How many black holes exist in the universe? Billions? Trillions? We are only beginning to count them. Intermediate mass black holes were supposed to be rare, between stellar mass, formed from collapsing stars, and supermassive, sitting at galaxy centers. The middle range, hundreds to hundreds of thousands of solar masses, should be uncommon. Theory predicted few formation mechanisms, but observations keep finding candidates. Dense star clusters harbor black holes of 10,000 solar masses. Dwarf galaxies host black holes of 100,000 solar masses. The intermediate mass range is more populated than models predicted. How do these black holes form? Runaway mergers in dense clusters? Direct collapse of massive gas clouds? Primordial black holes from the early universe? Each mechanism has problems, but the black holes exist. Supermassive black holes grow faster than we understand. Feed a black hole with gas and it radiates energy. The radiation pressure pushes against infalling gas, limiting the accretion rate. This is the Eddington limit, a fundamental constraint on black hole growth. Exceeding it should be impossible for long periods. Yet high redshift quasars contain billion solar mass black holes existing less than 1 billion years after the Big Bang. They grew at or above the Eddington limit continuously for nearly their entire existence. Possible? Barely, but requiring optimal conditions constantly. No interruptions, no gaps, just continuous maximal feeding. This seems unlikely. Either black hole seeds were much larger than we think, or growth exceeded the Eddington limit somehow. Super Eddington accretion might occur in special circumstances. If gas falls in along specific geometries, radiation can escape without pushing back on the infalling material as effectively. Thick accretion disks, radiation beamed in narrow cones, various configurations might permit faster growth. Simulations suggest this can work, but require fine-tuned conditions. Whether nature provides these conditions frequently enough to explain observations remains unclear. Primordial black holes offer another solution. If black holes formed directly in the early universe from density fluctuations, before any stars existed, they could have masses ranging from microscopic to millions of solar masses. 1 million solar mass seed at cosmic dawn could grow to 1 billion solar masses in 1 billion years without violating the Eddington limit. The problem is explaining why such massive primordial black holes would form. The density fluctuations required are larger than standard inflation predicts. Special inflationary models can generate them, but this requires adding complexity specifically to solve the high redshift quasar problem. Black hole mergers are more common than models predicted. LIGO and Virgo detect mergers of stellar mass black holes regularly now. The rate is higher than expected. Either binary black holes form more easily than we thought, or they merge more efficiently. Isolated massive stars collapsing to black holes should rarely be in tight enough binaries to merge within the universe's age. Most black hole binaries should drift apart, orbiting but never touching. Yet we detect dozens of mergers. This suggests formation channels we did not fully appreciate. Maybe black holes form in dense clusters where dynamical interactions bring them together. Maybe binary stars evolve in ways that keep black holes bound despite explosions and mass loss. The mechanisms are being worked out. Gravitational wave surprises continue. Some merging black holes have spins misaligned with their orbital plane. This indicates they did not form together as a binary pair from a single molecular cloud. They came together later, captured dynamically in dense environments. Other mergers show aligned spins, suggesting they did form together. The population is diverse. Multiple formation channels contribute. The statistical distribution of masses, spins, and merger rates constrain astrophysics in ways we could not before gravitational wave astronomy. Eccentric mergers are predicted, but not yet clearly detected. Most observed mergers have circular orbits, as expected from long evolution driven by gravitational wave emission. But if black holes scatter off each other in dense clusters, they can enter highly elliptical orbits before merging. These eccentric mergers would have distinctive gravitational wave signatures. Future detectors with better sensitivity should catch them. Finding eccentric mergers would prove that dynamical capture in clusters is a major formation channel. Neutron star mergers produce gold. When two neutron stars spiral together and collide, the explosion ejects neutron-rich material. Rapid neutron capture nucleosynthesis, the R process, occurs in this material. Heavy elements beyond iron, including gold, platinum, uranium, form in seconds. The 2017 neutron star merger, detected by LIGO, produced about 10 Earth masses of gold and platinum. Every gold atom in your jewelry, every platinum atom in catalytic converters came from neutron star mergers somewhere in the cosmic past. You wear the remnants of cataclysms that lit up distant galaxies with radioactive fire. But neutron star mergers are rare. Too rare perhaps to explain all heavy elements we observe. Some R-process elements might form in other sites. Certain types of supernovae, collapsing massive stars, might produce R-process elements. Magnetar outflows, highly magnetized neutron stars ejecting material, could contribute. The cosmic budget of heavy elements is being recalculated. Neutron star mergers are important but maybe not the only source. Nature is resourceful. Multiple mechanisms probably contribute. Neutron stars are stranger than we imagined. They are the densest matter in the universe that is not a black hole. A teaspoon of neutron star material weighs as much as a mountain. The cores might contain exotic states of matter, quark matter, where protons and neutrons dissolve into their constituent particles, or strange matter, stabilized by strange quarks, or superfluids, frictionless quantum liquids. We do not know what exists at nuclear densities. No laboratory can recreate these conditions. Neutron stars are natural laboratories, the only places in the universe where we can study matter at such extremes. The neutron star radius problem is ongoing. Measure a neutron star's mass from orbital dynamics. Measure its radius from X-ray emission. The ratio of mass to radius constrains the equation of state, the relationship between pressure and density in neutron star cores. Different observations give slightly different answers. Some suggest softer equations of state, more compressible matter. Others suggest stiffer equations of state, more resistant to compression. The discrepancies are not huge, but they are present. Reconciling all measurements requires careful modelling of neutron star atmospheres, magnetic fields, rotation, all complex and uncertain. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. These fields decay over thousands of years, releasing energy in occasional bursts. Magnetar flares are the brightest events in the universe besides supernovae and gamma-ray bursts. In 2004, a magnetar flare from 50,000 light-years away disrupted Earth's ionosphere. If a magnetar flared in our stellar neighbourhood within a few hundred light-years, the radiation could be catastrophic for life. Fortunately, magnetars are rare. Only about 30 are known in the Milky Way. The odds of one being nearby are low, but not zero. Fast radio bursts might come from magnetars. These millisecond flashes of radio waves from distant galaxies puzzled astronomers for years. No known phenomenon produced the right energy at the right timescales. Then in 2020, a fast radio burst was detected from a magnetar in our galaxy. This proved magnetars can produce FRBS, at least some of them. But the population of FRBS is diverse. Some repeat, some do not. Some have complex structures, others are simple pulses. Are all FRBS from magnetars, or do multiple mechanisms exist? The answer is still emerging. Repeating FRBS are particularly mysterious. One source, FRB 121102, has produced hundreds of bursts over years of observation. It cycles through active and quiet periods. The bursts come from a compact region, likely a magnetar, but surrounded by something that causes extreme scattering of the radio waves. What environment surrounds this object? A supernova remnant? The accretion disk of a black hole? A dense stellar cluster? Each model has problems. The environment must be extreme to produce the observed effects, yet also stable enough to persist for years without destroying the magnetar. The cosmic radio background is louder than expected. Add up all known radio sources, galaxies, quasars, everything that emits radio waves. The total should produce a certain level of background radio emission filling the universe. Observations show more background than accounted for. Where is the extra emission coming from? Faint sources below detection limits? A population of objects we have not characterized? Primordial magnetic fields? The discrepancy is small but real. Another mystery hiding in the data. Pulsars are cosmic clocks, neutron stars spinning rapidly, emitting beams of radiation from their magnetic poles. As the star rotates, the beam sweeps across space like a lighthouse. If Earth is in the path, we see a pulse. Some pulsars spin hundreds of times per second. The most stable pulsars rival atomic clocks for precision. Their pulse arrival times can be predicted years in advance to within microseconds. This stability makes pulsars useful for fundamental physics tests. Pulsar timing arrays detect gravitational waves, monitor dozens of pulsars for years. Gravitational waves passing through the galaxy change the distance to each pulsar slightly, altering pulse arrival times. By correlating timing changes across multiple pulsars, you can detect long wavelength gravitational waves from supermassive black hole mergers. The technique works for wavelengths comparable to the galaxy's size, complementing LIGO's sensitivity to shorter wavelengths. The first detection was announced recently. The signal is consistent with a background of countless supermassive black hole mergers throughout cosmic history. The gravitational wave background tells us about supermassive black hole populations. How many galaxies have merged? How often do central black holes merge after their host galaxies collide? Do black holes stall before merging, the final parsec problem, or do they coalesce efficiently? The amplitude and spectrum of the gravitational wave background answers these questions. Early measurements suggest black holes merge efficiently, more efficiently than some models predicted. The final parsec problem might not be a major obstacle, but uncertainties remain. More data will clarify the picture. Binary pulsars are gravitational physics laboratories. Two neutron stars orbiting each other, at least one emitting pulses. The orbit decays over time as gravitational waves carry energy away. Measure the decay rate, compare to general relativity predictions. The Hulse-Taylor pulsar matched predictions so precisely that it provided the first indirect evidence for gravitational waves decades before LIGO. Other binary pulsars have tested general relativity to even higher precision. So far, Einstein's theory passes every test. But general relativity is not complete. It cannot be the final theory. It does not incorporate quantum mechanics. At small scales or high energies, general relativity must break down. Quantum gravity, whatever form it takes, will replace general relativity just as relativity replaced Newtonian gravity. The question is not whether general relativity is wrong, it is where and how it fails. What regime reveals the breakdown? Black hole interiors? The Big Bang? Planck scale distances? We are searching for cracks. Gravitational lensing tests general relativity on cosmic scales, measure how mass bends light, compare to predictions. Discrepancies would indicate modified gravity. So far, observations match general relativity. Galaxies bend light exactly as predicted. Galaxy clusters produce lensing consistent with their mass. The cosmic microwave background lensing follows Einstein's equations. General relativity works on scales from solar system to cosmic horizon. This is extraordinary. No other theory in physics applies over so many orders of magnitude. Yet modified gravity theories keep being proposed. Not because general relativity fails tests, but because dark matter and dark energy seem ad hoc. Adding invisible matter and mysterious energy to make observations fit feels like epicycles, adding complexity to save a theory. Modified gravity attempts to explain observations without inventing new components. This is philosophically appealing. Occam's razor favours simpler explanations. But nature does not care about human aesthetic preferences. Simplicity is a guide, not a law. And so far, general relativity plus dark matter and dark energy fits observations better than any modified gravity theory. The cosmological constant problem remains the biggest embarrassment in theoretical physics. Quantum field theory predicts vacuum energy. Every quantum field contributes. Add up all contributions from all fields at all energies up to the Planck scale. The result is 10 to the 120 times larger than the observed cosmological constant. This is not close. This is not even in the right ballpark. This is catastrophically wrong. Something must cancel almost all the vacuum energy, leaving only a tiny residue. What mechanism achieves this cancellation? Supersymmetry would help. Every particle has a superpartner with opposite quantum statistics. The vacuum energy contributions from particles and superpartners cancel exactly if supersymmetry is unbroken. But supersymmetry is clearly broken. Superpartners have not been found. They must be heavier than ordinary particles, outside the range of current experiments. Broken supersymmetry does not cancel vacuum energy completely. Calculations still give results far too large. Supersymmetry reduces the problem but does not solve it. Anthropic reasoning offers an explanation. If infinite universes exist with different cosmological constants, we observe the one compatible with our existence. If the constant were much larger, galaxies would not form. If it were large and negative, the universe would recollapse before stars formed. We see a small positive value because that is the only type of universe where observers can evolve. This explains the observation, but makes no prediction. It says we are lucky. Or more precisely, we are selected. Only universes with observers contain observers to measure the cosmological constant. This reasoning is logically sound but scientifically sterile. Dynamical dark energy avoids anthropic reasoning. If dark energy is not a constant, but a field evolving toward a minimum, the field might relax to a small value naturally. The mechanism that brings it to the minimum operates in every universe. No anthropic selection required. This is more satisfying philosophically. But it requires inventing a new field with specific properties, fine. Tuned to solve one problem. The field must be light enough to matter today, but heavy enough not to have mattered in the early universe. Its potential must have the right shape. These requirements are restrictive. Many models have been proposed. None are compelling. The multiverse keeps appearing in cosmological discussions. Eternal inflation generates bubble universes. String theory predicts a landscape of possible vacuum states. Quantum mechanics might split into many worlds. Different mechanisms, different details, but the common theme is that our universe is not unique. Reality is vastly larger than the part we observe. This is either profound or absurd depending on your perspective. profound because it suggests the cosmos is richer and stranger than we imagined. Absurd because it postulates infinities of unobservable entities to explain observations. The multiverse might be real, or it might be the point where physics becomes metaphysics. Testability is the issue. Science requires testable predictions. A good theory predicts phenomena you can verify or falsify. The multiverse makes no testable predictions about other universes because they are unobservable by definition. It predicts only that we exist, which is not a prediction since we already know we exist. Some versions of the multiverse make statistical predictions about what typical observers should see. But these depend on how you count universes and observers, the measure problem, which has no agreed solution. Without testable predictions, is the multiverse science? Some physicists say yes. The multiverse is a consequence of well-tested theories like inflation and quantum mechanics. We do not observe other universes directly, but we did not observe quarks directly either when they were proposed. Quarks were inferred from patterns in particle physics. Other universes are inferred from cosmology and fundamental theory. This is legitimate scientific reasoning, and maybe someday we will find indirect evidence, fingerprints of other universes in our data, collisions during inflation, anomalies in the cosmic microwave background, something. Other physicists say no. The multiverse is unfalsifiable. It can accommodate any observation. Our universe has property X. Some universe in the multiverse has property X. This is not explanation. This is capitulation, admitting we cannot predict and declaring victory by saying anything goes. Science requires constraints. The multiverse removes constraints. It lets anything happen somewhere. This makes physics impotent. Better to admit ignorance than hide behind infinities. The debate continues without resolution. Perhaps future discoveries will force the issue. Evidence might emerge that clearly requires a multiverse, or might prove it wrong, or might leave the question permanently ambiguous. Science does not always provide definitive answers. Some questions remain open for generations. The multiverse might be one. Quantum mechanics interpretation is another permanently open question. The math works. Predictions match experiments. But what does it mean? The Copenhagen interpretation says quantum systems exist in superposition until measured. Measurement collapses the wave function. But what counts as measurement? Observation by a conscious mind? Interaction with? A macroscopic apparatus? Decoherence from entanglement with the environment? Different variants of Copenhagen give different answers. The many worlds interpretation eliminates collapse. Wave functions never collapse. Instead, reality splits into branches. Every quantum outcome occurs in some branch. All possibilities are realized. You exist in countless branches, experiencing different outcomes in each. This sounds like science fiction, but it is a mathematically consistent interpretation of quantum mechanics. It makes the same predictions as Copenhagen for all measurable quantities. You cannot experimentally distinguish them. Pilot wave theory brings back determinism. Particles have definite positions at all times, guided by a quantum wave. The wave evolves deterministically according to Schrödinger's equation. Randomness enters because we cannot know the initial particle positions precisely. This interpretation feels more intuitive. Particles are real objects, not smeared-out wave functions. But the pilot wave is non-local, influencing particles instantaneously across arbitrary distances. This bothers some physicists as much as wave function collapse bothers others. Objective collapse models modify quantum mechanics. Superpositions spontaneously collapse on their own without measurement. The collapse rate depends on mass. Microscopic systems remain in superposition for long times. Macroscopic objects collapse essentially instantly. This explains why we do not see superpositions of everyday objects. The collapse is a physical process, not dependent on observation. These models make slightly different predictions than standard quantum mechanics. Experiments are testing them. So far, standard quantum mechanics survives. But the tests continue. The quantum measurement problem is that we cannot agree what measurement is. This seems absurd. Quantum mechanics is the most successful theory in physics. It is nearly a century old. It has passed every experimental test. Yet physicists cannot agree on what it means. How can a theory be so successful yet so poorly understood? This should be humiliating. Instead, it has become normalized. Students learn to shut up and calculate, to use the math without worrying about interpretation. This works practically, but is intellectually unsatisfying. Quantum entanglement connects particles across the universe. Measure one entangled particle here. The measurement outcome appears instantaneously in a particle there, no matter how far apart. This seems to violate relativity, which says nothing travels faster than light. But quantum entanglement does not transmit information. You cannot control what measurement outcome you get, so you cannot send signals. The correlations exist but are only revealed after comparing measurements using slower-than-light communication. Relativity is not violated, but it feels like it should be. Quantum teleportation uses entanglement to transmit quantum states. Destroy a quantum state here, recreate it there. The original is obliterated. The copy is perfect. Nothing travels between locations except classical information. Yet the quantum state appears at the destination. This is not Star Trek teleportation. You cannot teleport matter or energy, only quantum information. Still, it is extraordinary and useful for quantum communication and quantum computing. Quantum cryptography guarantees secure communication. Eavesdropping introduces detectable errors. The laws of physics protect the message. No matter how sophisticated the eavesdropper, quantum mechanics reveals their presence. This is not encryption, which can be broken with enough computing power. This is fundamental security from the uncertainty principle. Systems are being deployed commercially. The technology works. Quantum physics is not just abstract theory. It enables practical technologies. Quantum computers will transform computation. A universal quantum computer could solve certain problems exponentially faster than classical computers. Factoring large numbers, simulating quantum systems, searching databases, optimization problems, drug discovery, material design. The applications are vast. The challenges are also vast. Building stable quantum computers requires isolating delicate quantum states from environmental noise. Progress is happening. Machines with hundreds of qubits exist, but scaling to millions of qubits needed for practical applications remains difficult. Quantum supremacy is the milestone where a quantum computer outperforms classical computers. Google claimed this in 2019 with a task designed to be easy for quantum computers, but hard for classical ones. IBM disputed the claim, arguing classical algorithms could match the performance. The debate illustrates the difficulty of comparing fundamentally different computational paradigms. Regardless, quantum computers are improving rapidly. Within decades, perhaps sooner, they will tackle problems beyond classical reach. Post-quantum cryptography is urgent. Current encryption relies on factoring large numbers being hard. Quantum computers can factor efficiently using Shor's algorithm. When large quantum computers exist, current encryption breaks. Secrets encrypted today could be stored and decrypted later, once quantum computers are available. This is a real threat. Governments and corporations are transitioning to post-quantum encryption algorithms that resist quantum attacks. The race is on. Will quantum-safe encryption deploy before quantum computers become powerful enough to threaten current systems? The universe is quantum. General relativity describes space and time. Quantum mechanics describes matter and fields. Both are extraordinarily successful in their domains, but they are incompatible. Combining them produces nonsense, infinities, breakdowns. A theory of quantum gravity is needed. String theory is one attempt. Loop quantum gravity is another. Other approaches exist. None are proven. None make testable predictions we can currently check. Quantum gravity might be the physics frontier for the 21st century, just as quantum mechanics and relativity were for the 20th. The Planck scale is where quantum gravity matters. At distances of 10 to the negative 35 meters, quantum fluctuations in spacetime become significant. At energies of 10 to the 19th gigaelectron volts, particle physics and gravity merge. We cannot reach these scales experimentally. The energies are a quadrillion times higher than the Large Hadron Collider achieves. No conceivable particle accelerator will probe the Planck scale directly. We need indirect methods. Cosmology provides one approach. The early universe reached Planck. Energies. Signatures might survive in the cosmic microwave background or gravitational wave background. Black holes are another quantum gravity laboratory. The singularity at the center is where general relativity predicts infinite density. Singularities should not exist. They signal theoretical breakdown. Quantum gravity should resolve the singularity, replacing it with something less pathological. String theory suggests the singularity is replaced by a string-scale structure. Loop quantum gravity suggests a bounce, avoiding singularity entirely. But we cannot observe black hole interiors. They are hidden behind event horizons. Testing quantum gravity in black holes is extraordinarily difficult. Hawking radiation offers a possible test. Black holes radiate due to quantum effects near the horizon. The radiation is thermal, temperature inversely proportional to mass. Solar mass black holes have temperatures a millionth of a degree above absolute zero, far too cold to detect. But primordial black holes, if they exist with masses near 10 to the 15th grams, would be hot enough to radiate significantly. They would evaporate today, producing bursts of gamma rays. Searches have found nothing. This constrains primordial black hole abundances. It does not test quantum gravity details, but confirms Hawking radiation principles. The information paradox haunts black hole physics. Quantum mechanics says information is never destroyed, but black holes seem to destroy information. Matter falls in, carrying information about its quantum state. The black hole eventually evaporates via Hawking radiation. The radiation is thermal, random, containing no information about what fell in. Where did the information go? This violates quantum mechanics. Either information is destroyed, contradicting quantum theory, or information escapes somehow, contradicting naive general relativity. Resolving this requires quantum gravity. Holography might be the answer. The holographic principle says all information in a volume is encoded on its boundary. A black hole's information is stored on the event horizon, not lost inside. As the black hole evaporates, information escapes in subtle correlations in the Hawking radiation. The radiation is not truly thermal, but contains hidden information. This preserves quantum mechanics, but it requires rethinking how spacetime and information relate. The horizon is not just a boundary, it is a data storage surface, a hologram encoding everything that fell into the black hole. The ADS/CFT correspondence is the most concrete realization of holography. Anti-de Sitter space, a negatively curved spacetime, is equivalent to a conformal field theory, a quantum theory living on its boundary. Gravity in the bulk equals quantum mechanics on the boundary. different descriptions of the same physics. This is profound. It suggests space-time might be emergent, not fundamental. At the deepest level, reality might be a quantum system without geometry. Space-time could be a useful approximation that breaks down at extreme scales. Emergence is a powerful idea. Temperature emerges from molecular motion. You cannot meaningfully talk about the temperature of a single molecule. Temperature is a property of large ensembles. Similarly, space-time might emerge from quantum entanglement. Individual quantum. States do not have geometry, but large networks of entangled states produce effective space-time. This would explain why quantum gravity is difficult. We are trying to quantize something that is itself quantum at a deeper level. The universe might be a quantum computer. Every particle, every interaction is a quantum operation. The cosmos computes its own evolution. This is not metaphor. This is literal. The universe processes quantum information according to physical laws. In this view, physics is computation. Understanding the universe means understanding the algorithm it runs. This perspective is still speculative but gaining traction. It connects information theory, quantum mechanics, and cosmology in new ways. Quantum cosmology applies quantum mechanics to the entire universe. The universe has a wave function. It exists in superposition of different geometries, different histories. Measurement is undefined because there is no outside observer. The Hartle-Hawking proposal suggests the universe wave function is the sum over all compact Euclidean geometries. This avoids the initial singularity. The Big Bang is replaced by a smooth quantum transition from nothing to something. Time emerges from the geometry. Before time, the concept of before is meaningless. This is where physics meets philosophy. What does it mean to apply quantum mechanics to the universe? If measurement requires an observer, who observes the universe? The Copenhagen interpretation breaks down. Many worlds might fare better. The universe splits into all possible branches. We observe one branch, others exist but are inaccessible. Or perhaps the interpretation question dissolves. Maybe quantum mechanics simply describes correlations. No collapse, no branches, just mathematical relations between subsystems. The universe is one big quantum state evolving unitarily forever. The anthropic principle returns. If the universe is quantum, all possible outcomes exist in superposition or in different branches. We observe the particular outcome compatible with our existence. This is unavoidable. We cannot observe outcomes where we do not exist. Selection effects are built into observations at the deepest level. This does not explain why the universe is life-friendly. It just acknowledges that we necessarily observe a life-friendly part. Fine-tuning persists as a mystery. The constants of nature appear precisely calibrated to allow complexity. Change the electron mass slightly, chemistry breaks. Change the strong force slightly, nuclei do not form. Change the cosmological constant more than slightly, galaxies do not form. Are these coincidences? Design? Anthropic selection from a multiverse? We do not know. The fine-tuning is real. The explanation is missing. Some physicists argue fine-tuning is overstated. Living beings are adaptable. Life might exist with very different physical laws. Carbon-based chemistry is not the only option. Silicon-based life, plasma-based life, exotic configurations we have not imagined might be possible. We assume life requires stars and planets because we only know one example. Maybe the space of life-permitting parameters is larger than we think. This is speculation. But it is worth remembering that arguments from ignorance are weak. We do not know how restricted the parameters must be. Other physicists argue fine-tuning points toward deeper principles. Maybe the constants are not independent. Maybe they are determined by a fundamental theory that makes only certain combinations possible. If a theory of everything exists, it might predict all constants from first principles. No free parameters, no tuning, just inevitable consequences of mathematical consistency. This is the dream of theoretical physics. One equation from which everything follows. No multiverse needed, no anthropics, just pure logical necessity. We are far from that dream. The standard model of particle physics has 19 free parameters, 19 numbers that must be measured experimentally because theory does not predict them. Particle masses, force coupling strengths, mixing angles, all arbitrary as far as we know. A deeper theory should explain these. String theory promises to, in principle, but has not delivered specific predictions. Other approaches also promise unification but remain incomplete. The theory of everything, if it exists, remains elusive. Maybe there is no theory of everything. Maybe the tower of theories never ends. Each theory is effective, valid at certain scales, breaking down at higher energies or smaller distances. Maybe physics is effective theories all the way down. No ultimate foundation, just approximations suited to different regimes. This is less aesthetically pleasing, but possibly more realistic. Nature is under no obligation to be simple at the deepest level. The universe surprises us constantly. Every time we build a better instrument, we find something unexpected. Pulsars, quasars, gamma-ray bursts, dark matter, dark energy, gravitational waves, fast radio bursts. The list grows. Each discovery was unanticipated. Theorists did not predict them. They emerged from data, forcing theory to catch up. This pattern will continue. Future telescopes will find phenomena we have not imagined. The universe is richer than our theories. The unknown unknowns are what drive science forward. The things we do not know, we do not know. Donald Rumsfeld made this phrase famous, but the concept is older. There are known knowns, things we know, known unknowns, things we know we do not know, and unknown unknowns, things we do not even know to ask about. Discovery happens in the third category. Asking better questions often matters more than answering existing questions. The Hubble tension might be an unknown unknown revealing itself. We thought we knew how to measure cosmic expansion. We were confident in our methods. Then the methods disagreed. This revealed a gap in our understanding we did not know existed. Something about the universe, some process or phenomenon, is affecting measurements in ways we did not anticipate. When we identify it, our knowledge will expand in directions we cannot currently predict. This is the pattern of scientific revolutions. Anomalies accumulate. Tensions grow. The old framework creaks under the weight of data that does not fit. Then someone proposes a new framework. Not just an adjustment, but a reconceptualization, a paradigm shift. The new framework explains the old data plus the anomalies. It makes new predictions. It opens new research directions. The revolution succeeds when evidence overwhelms resistance. We might be living through such a revolution. Cosmology's accumulating tensions might be symptoms of a deeper problem with the standard model. Dark matter and dark energy might be hints that we misunderstand gravity or quantum fields at cosmic scales. The Hubble constant discord might signal breakdown of assumptions we do not realize we are making. Future historians of science will look back at this era and see the clues. We are too close to see them clearly yet. Or maybe not. Maybe the tensions will resolve mundanely. Systematic errors will be found. Measurements will converge. The standard model will survive, validated by overcoming challenges. This has happened before. Anomalies that seemed revolutionary turned out to be experimental artifacts. We cannot know in advance which anomalies lead to revolutions and which to footnotes. Only time and evidence reveal the difference. What we can know is that the questions are important. Understanding cosmic expansion determines our place in space and time. Measuring structure formation reveals how complexity emerges from simplicity. Detecting dark matter connects particle physics to cosmology. Explaining dark energy might require new physics or reveal deep truths about quantum fields and gravity. These questions matter. Not for practical applications, at least not obviously, but for understanding reality. Science is humanity's tool for understanding reality, not the only tool. Art, philosophy, religion all offer insights. But science has a unique power. It makes testable predictions. It self-corrects through observation. It builds cumulative knowledge across generations. Science is not perfect. Scientists are human, prone to bias, error, groupthink. But the process, messy and imperfect as it is, slowly converges on truth. The universe is under no obligation to be comprehensible to human minds. That it is comprehensible, even partially, is miraculous. That primates evolved to throw rocks and recognize faces can understand cosmology, quantum mechanics, general relativity is astonishing. The universe did not optimize for being understandable, yet we can understand it. This gift should not be taken for granted. Every measurement, every observation, every data point is an opportunity to learn. Even when measurements disagree, especially when they disagree, we learn. Discrepancies reveal gaps in knowledge. They point toward unknown phenomena. They motivate better experiments, deeper theories, new questions. The Hubble tension is frustrating. It is also exhilarating. Something interesting is hiding in there, something we do not understand yet, and finding it will expand human knowledge in unpredictable ways. The calculation continues. It will always continue. We will measure the Hubble constant more precisely. We will test dark matter and dark energy more carefully. We will probe quantum gravity more deeply. Each answer will raise new questions. Each discovery will open new mysteries. This is not a problem. This is the nature of science. The frontier recedes as we approach it. Knowledge expands fractally. The more we know, the more we realize we do not know, but we keep trying. Because understanding matters, because curiosity drives us, because the universe is magnificent and worthy of study. We measure, we calculate, we theorize, we observe. We get things wrong. We correct ourselves. We get less wrong. Slowly, painfully, with many false starts and dead ends, we approach truth. We may never reach it completely, but the journey is worthwhile. This is the universe miscalculated. This is the crisis in cosmology. This is the story of measurements that do not agree and the search for why. The Hubble constant is wrong, or our measurement methods are wrong, or our understanding is incomplete. Something is wrong. We will figure out what. And when we do, the cosmos will make sense in a new way. Until then, we live with uncertainty, with tension, with the uncomfortable knowledge that our best measurements contradict each other. This is where we are. This is science in number sign. The universe miscalculated. The Hubble constant crisis. For 90 years, we measured the universe expanding at one speed. We calculated how fast galaxies fly apart, how quickly space stretches, when the Big Bang occurred. The number is called the Hubble constant, and it is the most important measurement in cosmology. It tells us the age of everything, the size of everything, the fate of everything. We thought we knew it. We were wrong. The universe is not expanding at the rate we calculated. Different measurements give different answers, and the disagreement is getting worse, not better. This is not a small error. This is a crisis that threatens to destroy our understanding of cosmic history. If you want to see how the most important number in astronomy fell apart, stay with us. This is the story of the Hubble tension, and it changes everything we thought we knew about the cosmos. Open your cosmology textbook, find the Hubble constant, the number that describes how fast the universe expands. For decades, we argued about whether it was 50 or 100 kilometers per second per megaparsec. Teams fought over measurements, careers were built and destroyed defending different values. Then technology improved. Measurements converged. By the year 2000, we thought we had it. 70 kilometers per second per megaparsec, give or take a few percent. Case closed. Problem solved. Except it was not solved at all. It was about to explode into the biggest crisis in modern cosmology. The Hubble constant works like this. Measure how fast a galaxy moves away from us. Measure how far away it is. Divide velocity by distance. That gives you the expansion rate. Do this for many galaxies at different distances. The pattern should be consistent. Farther galaxies should move faster in direct proportion to their distance. This is Hubble's law, discovered in 1929, the foundation of observational cosmology. Simple in principle, nightmarishly difficult in practice. Because measuring cosmic distances is hard, incredibly hard, and every error in distance measurement shows up in the Hubble constant. The distance ladder is how we measure the universe. Start with nearby stars. Use parallax, simple geometry. Watch them shift position as Earth orbits the Sun. This works for a few thousand light years, no more. Beyond that, you need standard candles, objects with known brightness. Measure how bright they appear, calculate how far away they must be. Cepheid variable stars are the first rung beyond parallax. These stars pulse with periods related to their luminosity. Measure the period, know the brightness, calculate the distance. Henrietta Swan Leavitt discovered this relationship in 1912, revolutionizing astronomy. For a century, Cepheids were the gold standard for measuring nearby galaxies. Type Ia supernovae are the next rung. These exploding stars reach consistent peak brightness, bright enough to see across billions of light years. Use Cepheids to calibrate nearby supernovae distances. Then use supernovae to measure distances to far galaxies where Cepheids are too faint to see. Each rung depends on the one before. Each calibration carries uncertainty forward. Errors accumulate. Small mistakes at nearby distances become huge errors at cosmic scales. This is the fundamental problem with the distance ladder. You are building a tower to measure the sky, and every brick you add makes the structure more unstable. The local measurement of the Hubble constant uses this distance ladder. The Hubble Space Telescope observed Cepheids in nearby galaxies, measuring distances with extraordinary precision. Then astronomers found Type 1a supernovae in those same galaxies, calibrating the supernova brightness. Finally, they observed supernovae in distant galaxies, calculating recession velocities and distances. The result, 73 kilometers per second per megaparsec, with an uncertainty of just 1%. This is a triumph of observational astronomy. Decades of work, thousands of measurements, sophisticated analysis. The team, led by Adam Rees, won a Nobel Prize for related work. Their measurement should be correct. It is built on solid physics, careful observations, rigorous statistics. The cosmic microwave background gives a completely different answer. This radiation, the afterglow of the Big Bang, fills the universe. The Planck satellite mapped it with exquisite precision, measuring temperature fluctuations to parts per million. These fluctuations encode information about the early universe, its density, composition, expansion rate. Feed the measurements into cosmological models. Calculate forward 13.8 billion years. The model predicts what the Hubble constant should be today. The answer, 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. This measurement is completely independent of the distance ladder. It uses different physics, different data, different analysis. It should agree with the local measurement. It does not. The disagreement is 6 kilometers per second per megaparsec, 6 times larger than the combined uncertainties. 9% does not sound like much. In everyday life, being 9% wrong is close enough. But in science, when two measurements disagree by multiple standard deviations, something is seriously wrong. At first, astronomers assumed systematic errors. Maybe the Cepheid calibration was off. Maybe dust obscured distant supernovae, making them appear fainter and therefore farther than they really were. Maybe the cosmic microwave background analysis had subtle mistakes. Teams checked everything: dust corrections, metallicity effects, selection biases, statistical methods. Every systematic error they found made the problem smaller by a fraction of a percent. The core disagreement remained. The two measurements kept giving different answers. The Hubble tension is what astronomers call this discrepancy. Tension is a polite word. Crisis is more accurate. One of these measurements must be wrong, or both are wrong, or our understanding of the universe is fundamentally flawed. There are no good options. The local measurement uses straightforward observations of stars and supernovae. The cosmic microwave background uses our best model of cosmic evolution. Both have been checked and rechecked. Both appear solid, yet they disagree. This is not how science is supposed to work. When careful measurements contradict each other, usually one is obviously flawed. Not this time. Both measurements are excellent. Both teams are competent. Both results are published in top journals. And they are irreconcilably different. New measurements made it worse. As instruments improved and uncertainties shrank, the disagreement became more pronounced, more undeniable. The Hubble constant should have converged. Different teams should have gotten the same answer within error bars. Instead, the local measurements cluster around 73, the early universe measurements cluster around 67, and the gap refuses to close. It is getting wider. This is alarming. It means the discrepancy is real, not a fluke, not measurement error, but something fundamental about the universe that we do not understand. Imagine measuring the same object from two different angles. You use different instruments, different methods, completely independent approaches. Both measurements should give the same answer. They do not. One says the object is 67 centimeters long. The other says 73 centimeters. The instruments are good. The methods are sound. The measurements are precise. What do you conclude? Either one instrument is miscalibrated in ways you have not detected, or the object changed size between measurements, or space itself works differently than you think. These are the options facing cosmologists. None of them are comfortable. Dark energy might be the culprit. This mysterious force drives cosmic acceleration, pushing galaxies apart faster over time. Standard models assume dark energy is constant, the same strength everywhere and always. But what if dark energy evolved? What if it was weaker in the early universe and grew stronger over time? This would make the early universe expand slower than we think. The cosmic microwave background would give a low Hubble constant because it measures expansion billions of years ago. The local universe would show a higher Hubble constant because expansion has accelerated. Variable dark energy could resolve the tension. But it would destroy the cosmological constant, the simplest explanation for dark energy. It would require new physics, new fields, new mechanisms. Physicists resist adding complexity without compelling evidence. Yet the Hubble tension is becoming compelling. Early dark energy is one specific proposal. A new field dominated the universe briefly after the Big Bang, then decayed away. This field changed the expansion rate in the early universe just enough to shift predictions from cosmic microwave background observations. The local universe never saw this field. It decayed billions of years ago. So local measurements give a different answer. This is speculative, untested, designed specifically to solve the Hubble tension. Critics call it ad hoc, inventing new physics to explain one anomaly. Supporters say it is a legitimate hypothesis that makes testable predictions. The debate continues. Modified gravity is another possible solution. Perhaps Einstein's general relativity is not quite right on cosmic scales. Small deviations from standard gravity could change how the universe expands. These deviations would affect early and late universe differently, creating apparent discrepancies in the Hubble constant. Many modified gravity theories exist. Most fail other observational tests. A few survive. Whether any can solve the Hubble tension while fitting all other data remains unclear. Modified gravity is a last resort. General relativity has passed every test for a century. Abandoning it is not done lightly. Extra radiation in the early universe could help. If more neutrinos or other light particles existed than standard models assume, they would change the expansion rate when the cosmic microwave background formed. This would shift predictions, potentially resolving the tension. But extra radiation should show up in other observations too. So far, no evidence has appeared. The cosmic microwave background itself constrains extra radiation tightly. There is little room for this solution to work. Measurement errors remain possible. Maybe there is a subtle systematic bias nobody has found. Maybe Cepheid distances are off in ways we do not understand. Maybe dust corrections are wrong. Maybe supernova physics is more complicated than we think. Teams have checked everything they can imagine. They keep finding nothing. But absence of evidence is not evidence of absence. Hidden systematics are always possible. The problem is, both measurements would need hidden errors, pulling in opposite directions by just the right amount. This seems unlikely. Conspiracy theories in data are rare. New physics is the exciting possibility. The Hubble tension might be telling us something profound about reality. Some unknown field, force, or phenomenon affects cosmic expansion in ways we have not imagined. This would be revolutionary. It would transform cosmology. It would win Nobel Prizes. But extraordinary claims require extraordinary evidence. Right now, the evidence is one discrepancy. Important, persistent, troubling, but still just one number that does not fit. Scientists need more. They need independent anomalies pointing the same direction, predictions that pan out, a coherent framework explaining everything. We are not there yet. The crisis deepens with every new measurement. Gravitational lensing offers an independent way to measure the Hubble constant. Observe a distant quasar lensed by a foreground galaxy. The light takes multiple paths around the galaxy, arriving at different times. Measure the time delays and the lens geometry, calculate the Hubble constant. This method does not use the distance ladder. It does not depend on cosmic microwave background models. It is completely independent. The results? Right between the other two measurements, about 70 kilometers per second per megaparsec, but with large uncertainties. As the uncertainties shrink, will lensing favor the local value, the early universe value, or something else entirely? Nobody knows. Gravitational waves provide yet another method. When black holes or neutron stars merge, they produce gravitational waves and sometimes electromagnetic signals. Measure the gravitational wave signal to determine distance. Measure the electromagnetic spectrum to determine recession velocity. calculate the Hubble constant. The LIGO and Virgo detectors have measured a few events. The uncertainties are still large, but they are shrinking. In a decade, gravitational wave measurements might resolve the Hubble tension, or they might deepen it, or they might split the difference, confusing everything further. Tip of the red giant branch offers another distance measurement technique. Old stars reach a peak brightness before fading. This peak is consistent across different galaxies. Measure it, calculate distances, determine the Hubble constant. Recent measurements using this method give values around 70 between the two extremes. But uncertainties are large and calibration is tricky. As more data accumulates, this method will either clarify or confuse the picture. The situation is this. We have multiple independent methods for measuring the Hubble constant. They all should agree. They do not. The disagreement is statistically significant. It persists despite intense scrutiny. It is getting worse, not better. Something is wrong. We do not know what. Maybe one measurement has subtle errors. Maybe the universe is more complicated than our models. Maybe new physics is revealing itself. The answer will reshape cosmology. But right now, we do not have the answer. We have a crisis. Universities are hosting conferences dedicated to the Hubble tension. Papers flood journals proposing solutions, testing hypotheses, analysing data. Young researchers are building careers on this problem. Established scientists are questioning assumptions they took for granted for decades. The field is in turmoil, productive turmoil, the kind that drives science forward. This is how paradigm shifts begin. A measurement that does not fit, an anomaly that will not go away, a crisis that demands resolution. The history of science is full of crises that led to revolutions. In the early 1900s, the orbit of Mercury did not match Newton's predictions. Astronomers tried everything to explain it. Maybe an unseen planet perturbed Mercury. Maybe the Sun was not perfectly spherical. Every solution failed. Then Einstein proposed general relativity, and the discrepancy vanished. Mercury's orbit was the first evidence that Newtonian gravity was not the final word. The Hubble tension might be similar. A crack in the foundation, a hint that our cosmological model is incomplete. Or maybe it is nothing. Maybe someone will find the systematic error. Maybe a calibration will be corrected. Maybe the tension will resolve itself without new physics. This has happened before. Anomalies that seemed revolutionary turned out to be mundane mistakes. Science is littered with false alarms, measurements that contradicted theory but eventually were explained within existing frameworks. The Hubble tension could be just another example, but the longer it persists, the more measurements confirm it, the less likely that becomes. The age of the universe depends on the Hubble constant. A higher expansion rate means a younger universe. The local measurement implies an age around 12.7 billion years. The cosmic microwave background implies 13.8 billion years. This difference matters. Some stars appear older than 13 billion years based on their compositions and evolutionary states. If the universe is only 12.7 billion years old, these stars cannot exist. They predate the universe itself. This is impossible. Either stellar age estimates are wrong, or the Hubble constant measurement giving a young universe is wrong, or something strange is happening. Globular clusters contain the oldest stars in the Milky Way. These tight balls of ancient stars orbit our galaxy's halo, formed when the universe was young. Dating them requires understanding stellar evolution, nuclear physics, observational astronomy. Current estimates put the oldest globular clusters at 12 to 13 billion years old. This fits comfortably with a 13.8 billion year old universe. It creates tension with a 12.7 billion year old universe. Not impossible, but uncomfortable. Everything needs to align just right. The margins are thin. White dwarf cooling provides another age estimate. These stellar remnants cool predictably over billions of years. Measure a white dwarf's temperature, and you can calculate how long it has been cooling. The coolest white dwarfs in the Milky Way appear to be around 12 to 13 billion years old. Again, comfortable with the cosmic microwave background age, tense with the local measurement age. The evidence is not definitive. Uncertainties exist, but the pattern is consistent. Multiple independent age estimates favor an older universe, supporting the cosmic microwave background measurement of the Hubble constant. Distant galaxies look surprisingly mature. The James Webb Space Telescope found galaxies at high redshift that appear too old and too massive for their age. If the universe is younger than we think, this problem gets worse. Less time means less time for galaxies to form, grow, accumulate stars. The early galaxy problem is already troubling. A younger universe makes it worse. This is not direct evidence for or against any Hubble constant value, but it adds context. The universe needs enough time for the structures we observe to form. If the expansion rate is higher, time is shorter, and formation becomes more difficult to explain. The cosmic distance ladder is being rebuilt. Gaia spacecraft measured parallaxes for over 1 billion stars with unprecedented precision. These measurements anchor the first rung of the ladder more securely than ever before. Every Cepheid distance now rests on better foundations. Systematic errors in parallax measurements are shrinking. This makes the local Hubble constant measurement more reliable, not less. It eliminates one possible source of error. Yet the tension persists. This is frustrating. When you fix a potential problem and the discrepancy remains, you run out of explanations. Cepheid metallicity affects their brightness. Stars with more heavy elements look slightly different than metal-poor stars. This has been known for decades. Corrections exist, but maybe the corrections are not quite right. Maybe metallicity effects are larger or more complex than we think. Teams are studying Cepheids in different environments with different compositions at different distances. So far, the metallicity effects appear to be well understood and properly corrected. This potential explanation does not seem to resolve the tension. Type 1a supernovae might not be perfect standard candles. These explosions occur when white dwarfs accrete mass from companions and reach a critical threshold, detonating catastrophically. The physics should be consistent. Every white dwarf should explode at the same mass, producing the same brightness. But observations show variations. Some supernovae are brighter, some fainter. Corrections exist based on light curve shapes and colours. But maybe the corrections miss subtle systematic effects. Maybe supernovae in different environments behave slightly differently. Maybe distant supernovae are not perfect analogues of nearby ones. Teams are studying this intensely. No smoking gun has appeared. Gravitational lensing by intervening matter affects supernova brightness. Light from distant supernova passes through cosmic structure, galaxies and dark matter, which focus or defocus the light slightly. This gravitational lensing changes the apparent brightness, introducing errors in distance estimates. The effect is small for individual supernovae, but could create systematic biases when averaged over many observations. Researchers are modelling this carefully, trying to quantify the impact. It does not appear large enough to explain the Hubble tension, but it is one more source of uncertainty. Selection biases haunt astronomical surveys. You observe the brightest objects most easily. Fainter objects get missed. This creates a bias toward bright objects in any sample. If supernova brightness has any systematic variation with distance or environment, selection effects could introduce errors. Teams work hard to correct for this, but it is difficult. You cannot correct for objects you did not observe because they were too faint. Some bias always remains. Whether it is large enough to matter for the Hubble constant is unclear. Dust extinction makes distant objects appear fainter. Cosmic dust absorbs and scatters light, reddening the spectrum and dimming the brightness. Corrections exist based on how much the light is reddened. But dust properties vary. Not all dust reddens light the same way. If distant dust differs systematically from nearby dust, corrections might be wrong. This has been checked extensively. So far, dust corrections appear solid, but it remains a possible source of hidden systematic error. The cosmic microwave background analysis is also being scrutinized. The Planck satellite produced extraordinary data, but the analysis is complex. Turning raw measurements into cosmological parameters requires sophisticated modeling. Assumptions about the early universe, about the physics of recombination when atoms formed, about the behavior of photons and baryons, all feed into the analysis. If any assumption is slightly wrong, the inferred Hubble constant shifts. Teams have checked these assumptions carefully. The standard model fits the data beautifully, but beautiful fits can be deceiving. Neutrinos affect the cosmic microwave background subtly. The number of neutrino species, their masses, how they interacted in the early universe, all change the predictions slightly. Standard models assume 3 neutrino types with small masses. If reality differs, if extra neutrino species exist or masses are different, the inferred Hubble constant changes. Particle physics experiments constrain neutrinos tightly. There is little room for surprises, but little room is not no room. Unexpected neutrino physics remains a possibility. Helium abundance provides an independent check on early universe conditions. The Big Bang produced hydrogen and helium in specific ratios determined by nuclear physics and the expansion rate. Measure helium abundance today, infer the conditions when it formed. This provides a consistency check on cosmic microwave background interpretations. So far, everything matches. The helium abundance predicted from cosmic microwave background measurements agrees with observed abundances. This supports the early universe measurement of the Hubble constant. It does not resolve the tension, but it adds confidence that cosmic microwave background analysis is not fundamentally flawed. Baryon acoustic oscillations are another piece of evidence. Sound waves in the early universe left imprints on how galaxies cluster today. Measuring these imprints reveals the universe's expansion history. The pattern depends on the Hubble constant. Observations of baryon acoustic oscillations favor the cosmic microwave background value around 67. This is independent evidence supporting the early universe measurement. The local measurement stands increasingly alone, contradicted by multiple lines of evidence, yet it refuses to go away. The distance ladder measurement is too solid, too carefully done, too thoroughly checked to dismiss. The SH0ES team, led by Adam Rees, has dedicated years to measuring the Hubble constant. They have observed hundreds of Cepheids, dozens of supernovae, checked systematic errors exhaustively. Their measurement is a masterpiece of observational astronomy. They are not making obvious mistakes. They are not ignoring known systematics. They are doing everything right. Yet their answer disagrees with the cosmic microwave background. This is what makes the Hubble tension so frustrating. Both sides are correct within their methodologies. The conflict is not between good and bad science. It is between two excellent measurements that happen to disagree. The Planck collaboration produced the cosmic microwave background data and analysis. This is also a masterpiece representing decades of work by hundreds of scientists. The satellite functioned beautifully. The data are pristine. The analysis is thorough. They are also doing everything right. Yet their answer disagrees with the distance ladder. Two groups of brilliant scientists using different methods, analysing different data, arriving at incompatible conclusions. This is the Hubble tension in its essence. Resolution will come eventually, more data will accumulate, new methods will be developed, independent measurements will multiply, the truth will emerge from the noise. But right now, we do not know what the truth is. We have two measurements, both excellent, both contradictory. One is wrong, or both are wrong, or the universe is more complicated than we think. These are the only options. The crisis is real, the implications are profound, and the answer, whatever it is, will reshape our understanding of the cosmos. The Hubble constant determines cosmic fate. If the universe expands slowly, gravity might eventually halt expansion and cause recollapse. If it expands quickly, galaxies fly apart forever, accelerating into infinite dilution. The boundary between these fates depends on the expansion rate and the density of matter and energy. We thought we knew which side of the boundary we occupy. The Hubble tension makes us question even this. If the expansion rate is different than we think, predictions about the far future change. Will galaxies remain visible billions of years from now? Will structures continue forming? Will the universe end in fire or ice or something else? The answer depends on getting the Hubble constant right. Dark energy measurements depend on the Hubble constant. To calculate dark energy's properties, you need to know the current expansion rate. Different Hubble constant values give different dark energy equations of state. This affects whether dark energy is constant, increasing, or decreasing over time. It changes predictions about when dark energy began. Dominating cosmic expansion. Every cosmological parameter is interconnected. The Hubble constant anchors them all. Get it wrong and everything shifts. The distance scale of the universe changes with the Hubble constant. A higher expansion rate means galaxies are closer than we think. A lower expansion rate means they are farther. This affects estimates of galaxy sizes, luminosities, masses, everything. The Andromeda galaxy sits about 2.5 million light-years away. Or does it? The distance depends on calibrations that tie back to the Hubble constant. If the expansion rate is wrong, the distance ladder is miscalibrated, and every distance in the universe needs adjustment. Cosmology is in crisis, but this is productive crisis. The field is energized, not paralyzed. Researchers are proposing solutions, testing hypotheses, gathering data. Conferences are packed, papers are flying, young scientists are excited. This is how science works best. A problem that cannot be ignored, a mystery that demands solution, a crisis that promises revolution if resolved. The Hubble tension might be the crack that shatters our cosmological model, or it might be a subtle systematic error that, once found, leaves the model stronger than before. Either way, the process of resolving it will teach us something fundamental about the universe. The James Webb Space Telescope is helping. It can observe Cepheids with better precision than Hubble. It can see farther, deeper, clearer. Early Webb observations have recalibrated some distance ladder rungs. The results? They confirm the local measurement. The tension persists. Webb is not resolving the crisis. It is clarifying that the crisis is real. This is valuable. False alarms are resolved quickly when new data arrives. Real problems persist. The Hubble tension is persisting. This tells us something important, even if we do not yet know what. The Roman Space Telescope will contribute. It will survey thousands of supernovae, measure distances to unprecedented precision, test the distance ladder more thoroughly than ever before. If systematic errors exist, Roman should find them. If the local measurement is correct, Roman will confirm it. If new physics is needed, Roman might provide clues. The mission launches in the 2030s. By then, the Hubble tension might be resolved through other means, or it might be worse. Either way, Roman will provide critical data. Gravitational wave astronomy is improving. More detectors are coming online. Sensitivity is increasing. The rate of detections is growing. Soon, gravitational waves will routinely measure the Hubble constant independently. This will break the tie between distance ladder and cosmic microwave background. Or it will create a three-way contradiction, which would be even more interesting. Gravitational waves are cosmology's newest tool. They are already transforming the field. Their impact on the Hubble tension will be significant. New theoretical frameworks are being proposed constantly. Modified gravity theories, evolving dark energy models, early dark energy, extra radiation, interacting dark sectors, the list goes on. Most will fail observational tests. A few might survive. One might be correct. Theorists are doing their job, generating testable hypotheses, providing options for observers to check. The interplay between theory and observation drives science forward. Right now, observations have presented a puzzle. Theory is trying to solve it. This is the scientific method in action. The Hubble constant is the most important number in cosmology, and we do not know what it is. Not precisely, not confidently. We have two excellent measurements giving different answers. This is the Hubble tension. It is the defining crisis of modern cosmology. How it resolves will determine the field's direction for decades. New physics? Subtle systematics? Measurement errors? The answer is coming. Data are accumulating. Methods are improving. The crisis will not last forever. But right now, in this moment, we live in a time of deep uncertainty about something fundamental. We do not know how fast the universe expands. And until we figure it out, every cosmological conclusion rests on shaky ground. This is the Hubble tension. This is the crisis. This is the most important problem in cosmology today. The universe is expanding. We have measured the rate. We have measured it again. The measurements disagree. Something is wrong. We will find out what. And when we do, when the Hubble tension finally resolves, we will understand the cosmos more deeply than we do today. That moment is coming. The work continues. The measurements improve. The crisis deepens. And somewhere in the data, the answer is waiting to be found. The universe miscalculated. Or rather, we miscalculated the universe. One of our fundamental measurements is wrong. The Hubble constant does not match. Different methods give different answers. This should not happen. Careful science should converge on truth. Instead, we have divergence, contradiction, crisis. But crisis drives progress. Comfortable certainty breeds complacency. Uncomfortable disagreement breeds innovation. The Hubble tension is uncomfortable. It is also exhilarating. Because when it resolves, however it resolves, we will know something new, something profound, something that transforms how we see the cosmos. And that moment, that revelation, that breakthrough is what every scientist lives for. The calculation continues. More telescopes observe, more data accumulate, more theories are proposed and tested. The Hubble constant will be measured again and again until the measurements agree. The tension will be resolved, the crisis will end, and cosmology will move forward, armed with better understanding, more precise measurements, deeper knowledge of the universe that birthed us and surrounds us, and will outlast us by trillions of years. This is the story of the Hubble tension. This is the crisis that defines our era. This is the problem that will not go away until we solve it. And we will solve it, because that is what scientists do. We measure, we calculate, we recalculate, we measure again. and eventually, finally, we get it right. But the Hubble tension is not the only measurement crisis facing cosmology. It is just the most famous, the most urgent, the most discussed. There are others, quieter problems, discrepancies that do not make headlines but keep astronomers awake at night. Each one is a crack in the foundation. Each one suggests our cosmological model might be incomplete. Together, they paint a picture of a field in transition, a science on the verge of transformation. Let me tell you about the other problems, the ones hiding in the shadows, waiting to explode. The sigma-8 tension measures how clumpy the universe is. Look at large-scale structure, the distribution of galaxies across cosmic volumes. Some regions have many galaxies, others are nearly empty. The degree of clumpiness depends on how much matter exists, how strongly it clumps under gravity, how long structure has been growing. Cosmological models predict a specific amount of clumpiness. Observations measure actual clumpiness. They disagree. Not as dramatically as the Hubble tension, but significantly enough to worry experts. Weak gravitational lensing measures sigma-8 directly. Observe how matter between us and distant galaxies bends light. More matter means more bending. More clumping means stronger variations in bending across the sky. Measure these variations statistically across millions of galaxies. Calculate how clumpy the universe is. Multiple surveys have done this. The Dark Energy Survey, the Kilo Degree Survey, the Hypersuprime Cam Survey, all find the same pattern. The universe is less clumpy than the cosmic microwave background predicts. About 8% less clumpy. This is the sigma-8 tension. 8% might not sound dramatic, but these are percent-level measurements. The uncertainties are small. The disagreement is statistically significant. Something is suppressing structure formation, or the early universe conditions were different than we think, or our understanding of how structure grows is incomplete. Each option has profound implications. Structure formation is gravity in action. If we get gravity wrong on cosmic scales, everything changes. Galaxy cluster counts also reveal sigma-8. Clusters form where structure is most developed, where matter has collapsed into the densest concentrations. Count clusters as a function of mass and redshift. Compare to predictions. Clusters are slightly less abundant than models suggest. Again, the universe appears less clumpy than expected. This is independent evidence for the same problem. Weak lensing and cluster counts use different physics, different data, yet point to the same conclusion. The standard model predicts too much structure. Neutrino masses might explain the sigma-8 tension. Massive neutrinos stream through the universe at high speeds, smoothing out small-scale structure. They prevent matter from clumping as efficiently as it otherwise would. If neutrinos are more massive than we think, they suppress structure more, reducing sigma-8 to match observations. Particle physics experiments constrain neutrino masses tightly. The room for maneuver is small, but small might be enough. Neutrino masses sit right at the edge of what could solve sigma-8 without violating particle physics constraints. Modified gravity could also explain sigma-8. If gravity is slightly weaker on cosmic scales than general relativity predicts, structure grows more slowly. This reduces clumpiness naturally. Several modified gravity theories make precisely this prediction. They strengthen gravity at small scales to explain galaxy rotation without dark matter, and weaken it at large scales to suppress structure formation. Whether any specific theory fits all observations remains debatable, but the pattern is suggestive. Baryonic feedback is the mundane explanation. When stars form, they produce powerful winds. When massive stars explode as supernovae, they blast gas out of galaxies. Supermassive black holes at galaxy centers produce jets that heat surrounding gas, preventing it from cooling and forming stars. All these processes, collectively called baryonic feedback, reduce how efficiently matter clumps into galaxies. Maybe simulations underestimate feedback. Maybe it is stronger than we think, suppressing structure formation enough to explain observations. This would solve sigma 8 without new physics. But it requires feedback to be precisely calibrated, stronger in reality than our best models suggest. That is possible, but it feels like fine-tuning. The lithium problem has haunted cosmology for decades. The Big Bang produced hydrogen, helium, and tiny amounts of lithium through nuclear reactions in the first few minutes. The abundances depend on the density of normal matter and the expansion rate during nucleosynthesis. Observations of the cosmic microwave background tell us the baryon density precisely. Plug it into Big Bang nucleosynthesis calculations. Out comes a prediction for primordial lithium abundance. Measure lithium in the oldest stars. Compare to predictions. Observations show 3 times less lithium than predicted. This is the lithium problem. It has persisted for 30 years. Nobody knows why. Maybe lithium is destroyed in stars. Even the oldest stars have interiors hot enough to burn lithium through nuclear reactions. If lithium from the stellar surface mixes into the hot interior, it gets destroyed. Models suggest this should not happen efficiently in low-mass stars. But maybe the models are wrong. Maybe mixing is stronger than we think. Maybe lithium depletion is more efficient. This would explain why observed abundances are low. But it requires stellar physics to conspire in just the right way. Many astronomers are skeptical. Maybe the primordial lithium abundance was never high. Perhaps Big Bang nucleosynthesis did not produce as much lithium as standard models predict. But why? The nuclear physics is well understood. The reaction rates are measured in laboratories. The baryon density is known from the cosmic microwave background. Change any parameter to reduce lithium production, and you destroy agreement with hydrogen and helium abundances, which match predictions beautifully. Lithium alone is anomalous. This makes no sense. Exotic physics in the early universe could explain it. If unknown particles or fields existed during nucleosynthesis, they could alter the conditions enough to suppress lithium production without affecting other elements significantly. This requires new physics tuned precisely to solve one problem while leaving everything else intact. Theorists have proposed dozens of models. None are compelling. The lithium problem remains unsolved, a thorn in the side of Big Bang cosmology, a reminder that even our most successful theories have unexplained anomalies. The Milky Way satellite plane is another puzzle. The small galaxies orbiting our galaxy are not randomly distributed. They lie preferentially in a thin plane, like a disk, all orbiting in the same direction. This is strange. Satellites should be scattered randomly in all directions if they fell into our gravitational well from random directions in space. Instead, they are organized. Andromeda has a similar satellite plane, so do some other large galaxies. This pattern appears too common to be coincidence. Cosmological simulations do not predict satellite planes. When you simulate galaxy formation, satellites accrete from all directions. They orbit chaotically. Occasionally, a plane forms by chance, but rarely, and it does not persist. Observed satellite planes are too thin, too coherent, too long-lived compared to simulations. This is the satellite plane problem. It suggests something about galaxy formation is not captured in simulations, or dark matter behaves differently than assumed, or we are missing some physical process. Tidal streams might explain satellite planes. If a large galaxy fell into the Milky Way billions of years ago, it could have brought multiple smaller satellites with it. These satellites would inherit the orbital plane of their parent galaxy, creating a disk-like distribution. This is possible, but requires specific timing and geometries. Not every galaxy could form satellite planes this way, yet many galaxies appear to have them. Either we are lucky, observing an unusual epoch, or the mechanism is more common than simulations suggest. Modified gravity makes a bold prediction about satellite planes. MOND, Modified Newtonian Dynamics, predicts that satellites falling into a galaxy should settle into preferred orbital planes, naturally due to the modified force law. This is a testable difference between MOND and dark matter models. Dark matter predicts random satellite distributions. MOND predicts planes. Observations appear to favour MOND in this case. This does not prove MOND is correct. Simulations might be missing physics that also produces planes in dark matter models, but it is a success for an alternative theory that mainstream science mostly rejects. The Fornax cluster timing problem is subtle but troubling. Fornax is a dwarf galaxy orbiting the Milky Way. It contains 5 globular clusters, ancient balls of stars. These globular clusters orbit within Fornax, but they should have sunk to the centre of Fornax due to dynamical friction, the gravitational drag from dark matter. Simulations show this happens quickly, within a few billion years. Yet Fornax's globular clusters are still spread throughout the dwarf galaxy. They have not sunk to the centre. This is the timing problem. Either Fornax has much less dark matter than expected, making dynamical friction weak, or the globular clusters formed recently, which seems unlikely, or our understanding of dynamical friction is wrong. The cuspy halo problem returns in different form. Dark matter simulations predict galaxy halos should have dense cores, cusps, where density increases steeply toward the center. Observations of dwarf galaxies show cores are less dense than predicted, more uniform, cored rather than cuspy. This discrepancy has existed for 20 years. Explanations involve baryonic feedback, supernovae explosions blowing dark matter out of galaxy centers, reducing the cusp. But dwarf galaxies have so little baryonic matter that feedback should be weak. How do you blow dark matter around with almost no normal matter to drive explosions? It is unclear. Self-interacting dark matter solves the cuspy halo problem naturally. If dark matter particles scatter off each other, they transfer energy, heating the core, puffing it up, reducing the cusp. The required interaction strength is small, far weaker than dark matter interactions with normal matter, but not zero. This fits observations well, but self-interacting dark matter creates problems elsewhere. Galaxy cluster cores should be smoother than observed. The bullet cluster, where 2 clusters collided, constrains self-interaction strength tightly. Thread the needle between fixing dwarf galaxies and not breaking cluster observations is difficult. Possible, but difficult. The too big to fail problem is related. Simulations predict massive subhalos orbiting galaxies like the Milky Way. These subhalos should host bright dwarf galaxies. They are too massive to fail at forming stars. Yet the observed dwarfs are much fainter than expected given their subhalo masses. Either the massive subhalos do not exist, contradicting simulations, or they failed to form stars, despite being massive enough that star formation should be inevitable. Neither option is comfortable. Ionization suppressing star formation helps explain too big to fail. After the first stars formed, their ultraviolet radiation ionized hydrogen throughout the universe. This heated the gas, giving it more energy, making it harder for gravity to pull gas into small halos and form stars. Dwarf galaxy halos in particular would be affected. Gas would be too hot to collapse efficiently. Star formation would be suppressed. This could explain why massive subhalos host unexpectedly faint dwarfs. They have the dark matter mass, but could not accumulate enough baryons to form many stars. This explanation is popular, but not proven. The missing baryons problem plagued cosmology for years. Add up all the normal matter in stars, gas, dust, everything we can see. The total is less than predictions from Big Bang nucleosynthesis and the cosmic microwave background. About 30% of baryons were missing. Where did they go? This mystery persisted until recently. The missing baryons were found hiding in plain sight. The warm, hot intergalactic medium contains the missing baryons. Between galaxies filling cosmic voids and filaments sits gas at temperatures of 100,000 to 10 million degrees. Too hot to form stars. Too diffuse to emit much radiation. Nearly invisible to most instruments. But it is there, in enormous quantities, carrying the missing baryons. X-ray observations and ultraviolet absorption line studies detected this gas. The accounting now balances. All predicted baryons have been found. The missing baryon problem is solved. But it took decades to solve because the gas hid where we were not looking carefully. The Hubble constant is not the only fundamental number in crisis. The fine structure constant, alpha, might vary across the universe. This constant determines the strength of electromagnetic interactions. It should be the same everywhere and always. That is what fundamental constant means. But some observations of distant quasars suggest alpha was slightly different billions of years ago. The changes are tiny, parts per million, but statistically significant in some datasets. Other datasets show no variation. The situation is murky. If alpha varies, the implications are revolutionary. Fundamental constants are supposed to be constant. They are part of the bedrock of physics. If they change with time or location, we need to explain why. What mechanism allows constants to vary? How does it work? What other constants vary? Is the speed of light constant? Is the gravitational constant constant? Once you admit one constant can change, everything becomes questionable. Most physicists are skeptical of varying constants. The evidence is weak and contested, but it cannot be ignored entirely. The cosmic coincidence problem asks why dark energy and dark matter have similar densities today. Dark matter density dilutes as the universe expands. More volume, same amount of matter, lower density. Dark energy density, if it is the cosmological constant, stays constant even as volume increases. In the past, dark matter dominated. In the future, dark energy will dominate. Only now, only in our epoch, are they comparable. Why? Is it coincidence? Or is there a connection between dark matter and dark energy that causes their densities to track each other? Anthropic reasoning offers one answer. If dark energy dominated earlier, galaxies would not have formed. Accelerated expansion would have prevented structure formation. Life requires galaxies, stars, planets, so we necessarily observe a universe where dark energy became important recently, after galaxies formed. This explains the coincidence through selection bias, but it feels unsatisfying. It replaces a physics explanation with an observational selection effect. Quintessence, a dynamical dark energy field, offers another answer. If dark energy is not constant but evolves, perhaps it tracks matter density. Maybe there is a mechanism that keeps dark energy and matter in rough balance. This requires specific field properties, carefully tuned potentials, but it is possible. Quintessence models make predictions about how dark energy changes over time. Observations are beginning to constrain these models. So far, a simple cosmological constant fits data best. But the search continues. The axis of evil in the cosmic microwave background refuses to go away. Several features in the temperature map align with each other and with the ecliptic plane of the solar system. The quadrupole and octopole, mathematical descriptions of large-scale patterns, point in nearly the same direction. This direction is suspiciously aligned with Earth's orbit. The universe should not care about Earth's orbit. This alignment should not exist, yet it does. Multiple analyses confirm it. Is it a statistical fluke, systematic error, or something genuinely anomalous? Systematic errors are the most likely explanation. The cosmic microwave background is faint. Foreground contamination from our galaxy is strong. Removing this contamination requires modelling and subtracting emission from dust, synchrotron radiation, free emission, everything in the Milky Way that glows at microwave frequencies. Maybe the foreground removal is imperfect. Maybe residual contamination creates false alignments. But multiple teams using different methods all see the same patterns. If it is systematic error, it is subtle and persistent. The cold spot is another cosmic microwave background anomaly. A region about 10 degrees across is significantly colder than surrounding areas. The temperature difference is only 0.00015 degrees, but on a map of 0.00003 degree fluctuations, it stands out. The cold spot is about 5 times larger than expected from random fluctuations. Its existence is not impossible, just unlikely. About 1 in 1,000 random universes would have such a cold spot. We might be the one. Or the cold spot might be real structure. Perhaps an enormous supervoid, a region with fewer galaxies than average, sits between us and the cosmic microwave background. Photons travelling through the void lose energy, emerging colder than average. This imprints a cold spot on the CMB. Observations have found a supervoid in roughly the right location, but it is not quite big enough to explain the full temperature deficit. Either there is more structure we are missing, or additional effects contribute. The hemispherical asymmetry is more troubling. One half of the sky shows higher temperature fluctuations than the other half. The difference is small, about 2%, but statistically significant. The universe should be isotropic. No preferred direction should exist. Yet observations suggest the universe is slightly lopsided. Some cosmological models predict this if the universe is finite and we can see a significant fraction of it. Fluctuations would not average out completely. We would see gradients, asymmetries, edges of modes that extend beyond our horizon. But standard inflation predicts the universe is vastly larger than the observable patch. We should see perfect isotropy. We do not. The lithium problem, the satellite plane problem, the timing problems, the cuspy halo problem, the too big to fail problem, the axis of evil, the cold spot, the hemispherical asymmetry, the sigma-8 tension, the Hubble tension. The list grows. Each problem is individually explainable. Maybe it is systematic error. Maybe it is bad luck. Maybe it is unusual but not impossible. But together they form a pattern of observations that do not quite fit the standard model. Not one catastrophic failure, but many small tensions. This is what revolutions look like in their early stages. Not a single dramatic falsification, but accumulated anomalies that collectively suggest something is wrong. History teaches us to pay attention to anomalies. Mercury's orbit did not fit Newtonian gravity. A tiny discrepancy, arc seconds per century, easy to dismiss. But it was real, and it led to general relativity. The photoelectric effect did not fit classical electromagnetism. Shining light on metal ejects electrons. The energy depends on frequency, not intensity. Weird, but easy to ignore. Until it led to quantum mechanics. The anomalous magnetic moment of the electron disagreed with Dirac's equation. A tiny effect, but it led to quantum field theory. Science progresses by explaining anomalies. Comfortable agreement with predictions is stable but boring. Discrepancies are uncomfortable but fruitful. Cosmology has a good track record of solving problems. The horizon problem, why distant parts of the universe have the same temperature despite never having been in causal contact, was solved by inflation. The flatness problem, why the universe is so close to critical density, was solved by inflation. The monopole problem, why magnetic monopoles predicted by grand unified theories do not exist, was solved by inflation. Inflation is the poster child for theoretical cosmology. It solved multiple problems with one elegant mechanism. Maybe a similar breakthrough awaits. Maybe one new idea will explain the Hubble tension, the sigma-8 tension, the lithium problem, all the accumulating anomalies. Or maybe each problem requires its own solution. Or maybe we need multiple new ideas working together. Dark matter is still not detected directly. 60 years after its discovery, we infer its existence from gravitational effects but cannot catch it in a laboratory. Dozens of experiments have searched. Detectors buried deep underground waiting for dark matter particles to collide with atomic nuclei. Satellites looking for gamma rays from dark matter annihilation. Particle colliders trying to create dark matter in high-energy collisions. Every experiment has found nothing. The parameter space is shrinking. If dark matter is WIMPs, weakly interacting massive particles, they should have been detected by now. Either they interact even more weakly than predicted, or they are not WIMPs. Alternative dark matter candidates multiply. Axions, sterile neutrinos, primordial black holes, self-interacting dark matter, fuzzy dark matter, the list is long and growing. Each candidate solves some problems and creates others. None fit all observations perfectly. This is frustrating. We know dark matter exists. We measure its gravitational effects constantly, but we do not know what it is. After 60 years, we still do not know. This is humbling. Modified gravity refuses to die. Despite decades of criticism, despite failing many observational tests, Maunder and its relativistic extensions keep being discussed. Why? Because they explain galaxy rotation curves better than dark matter. The relationship between visible matter and rotation velocity is tighter in MOND than in dark matter models. This is called the radial acceleration relation. It holds for hundreds of galaxies across wide ranges of mass and size. Dark matter models reproduce this relation but do not explain why it exists. It emerges from the data without theoretical justification. MOND predicts it from first principles. This is a point in MOND's favour. But MOND fails for galaxy clusters. It cannot explain the mass discrepancy in clusters without adding dark matter anyway. So MOND does not truly eliminate dark matter, just reduces how much is needed. And MOND cannot explain the cosmic microwave background or large-scale structure without modifications that make it as complicated as dark matter models. Most physicists conclude MOND is wrong, but a dedicated minority continues developing the theory. And occasionally, MOND succeeds where dark matter struggles. The satellite plane problem, the radial acceleration relation, certain aspects of galaxy dynamics. These successes keep the theory alive. The lesson is that alternative ideas, even rejected ideas, should not be completely abandoned. Science history is full of theories dismissed then later vindicated. Continental drift was mocked for decades before plate tectonics proved it correct. The Big Bang was controversial until the cosmic microwave background was discovered. Heliocentrism was heresy before telescopes confirmed it. Today's rejected theory might be tomorrow's revolution. Probably not. Most rejected ideas are rejected for good reasons, but possibly. Maintaining intellectual humility means keeping an open mind even toward ideas you think are wrong. The universe is more complicated than our models. This is always true. Models are simplifications, approximations, useful fictions. Newtonian gravity is not true, but it is accurate enough for most purposes. General relativity is probably not the final theory of gravity, but it is accurate enough for everything we have tested so far. The standard model of cosmology is probably not complete. It has too many free parameters, too many unexplained coincidences, too many tensions with observations. But it is accurate enough to describe most of cosmic history from seconds after the Big Bang to the present. That is remarkable. That is success. That is also not enough. Science demands more than approximate success. Science demands explanation. Why are parameters what they are? Why do coincidences occur? Why do tensions exist? These questions drive research. They motivate new theories, new observations, new experiments. The questions are harder than the measurements. Measuring the Hubble constant is difficult but straightforward. Explaining why different methods give different answers is much harder. It requires deep understanding of systematics, physics, perhaps even new phenomena we have not imagined. The James Webb Space Telescope was supposed to clarify cosmology. It was supposed to observe the earliest galaxies, test models of galaxy formation, resolve lingering questions. Instead, it raised new questions. Galaxies at high redshift are more massive than predicted. Stars formed earlier than expected. Supermassive black holes existed sooner than thought possible. Every prediction was slightly wrong. Not catastrophically wrong, just wrong enough to be uncomfortable. Webb is succeeding, finding what we did not expect, forcing us to rethink assumptions. This is what great instruments do. They surprise us. The cosmic web is more complex than simulations predicted. Filaments connecting galaxy clusters are thinner and longer than models suggested. Voids are emptier. The distribution of matter on large scales is lumpier in some ways, smoother in others. Simulations match overall statistics but miss fine details. Maybe this is just simulation resolution. Maybe we need more computing power, better algorithms, refined physics. Or maybe we are missing something fundamental about how structure forms. Magnetic fields thread the cosmic web. This was not expected. Magnetic fields should be weak in intergalactic space, but observations detect them far from galaxies, filling voids and filaments. Where do these magnetic fields come from? How did they get there? Galaxies eject magnetized gas, but can that explain magnetic fields in cosmic voids far from any galaxy? Primordial magnetic fields from the early universe offer another explanation. But generating strong fields in the Big Bang requires exotic physics. The origin of cosmic magnetic fields is an unsolved problem. Cosmic rays are another mystery. High-energy particles, mostly protons, bombard Earth from space. Some have energies exceeding anything we can produce in accelerators. One cosmic ray detected in 1991 had energy equivalent to a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. This is impossible to explain with known astrophysics. What accelerates particles to such energies? Supernova remnants, black hole jets, colliding galaxies, all are proposed sources. But the most energetic cosmic rays cannot travel far through space. They interact with cosmic microwave background photons, losing energy rapidly. They must come from relatively nearby, yet we see no obvious sources. The universe is full of mysteries hiding in plain sight. Dark matter is the biggest. Dark energy is second. But dozens of smaller mysteries litter the field. Each one is a potential crack in the foundation. Each one might be the thread that, when pulled, unravels everything. Or each might be explained mundanely, systematically, without revolution. We do not know until we investigate. So we investigate. We observe, we measure, we calculate, and sometimes we find that our measurements do not agree, that our calculations produce contradictions, that the universe refuses to fit our models. This is where we are. Cosmology is the most successful it has ever been. We understand the universe from microseconds after the Big Bang to the present. We can simulate galaxy formation, predict cosmic microwave background patterns, explain element abundances. Our knowledge is vast. Our models are sophisticated. Our instruments are powerful. And yet, fundamental measurements disagree. The Hubble constant does not match. Sigma 8 is too high. Lithium is too low. Satellites orbit in planes. The cosmic microwave background has anomalies. Dark matter is undetected. Every success is shadowed by lingering problems. The problems might be opportunities. Each discrepancy is a chance to learn something new. Each tension is a window into physics we do not understand. If the Hubble constant really is different when measured different ways, that tells us something profound about the universe. If sigma 8 is really too high, that reveals something about structure formation. If lithium is really depleted, that constrains stellar physics or early universe conditions. Problems are data. Data are valuable, even when the data say you are wrong. Being wrong is painful. Scientists are human. We prefer being right. We defend our ideas, sometimes too strongly. We resist change, sometimes too long. But ultimately, evidence wins. Data overwhelm denial. Measurements force revision. This is the strength of science. Not that scientists are objective, we are not. But science as a collective enterprise, as a social process, as an accumulation of evidence over generations, eventually gets things right. Slowly, reluctantly, with many false starts, but eventually. The revolution is coming. Maybe in 5 years, maybe in 50, but it is coming. Too many measurements disagree. Too many anomalies accumulate. Too many questions lack answers. The standard model of cosmology will be replaced by something better, something that explains more, predicts more accurately, resolves the tensions. That model might look similar to the current model, just refined, adjusted, improved, or it might be completely different, a paradigm shift that makes us wonder how we missed it for so long. Future generations will look back at our era and see the clues we overlooked. They will shake their heads at our blindness, our stubbornness, our attachment to models that obviously did not fit all the data. They will find it amusing that we argued for decades about the Hubble constant when the answer was right there, hiding in some dataset we collected but misinterpreted. They will have better instruments, deeper theories, clearer hindsight, and they will face their own crises, their own tensions, their own measurements that refuse to agree. This is the cycle of science. Build models, test predictions, find discrepancies, refine models, test again, find new discrepancies. The process never ends. Truth is asymptotic. We approach it but never quite reach it. Each generation gets closer, understands more deeply, sees more clearly. But there is always farther to go, always more to learn, always another mystery waiting beyond the current frontier. The Hubble constant is wrong, or the way we measure it is wrong, or our understanding of what it means is wrong. Something is wrong. We do not know what, but we will find out. Because that is what scientists do. We find cracks in our knowledge and we investigate them. We pry them open, shine lights into the darkness, see what is hiding underneath. Sometimes we find nothing, just our own mistakes. Sometimes we find everything, revelations that transform our worldview. The universe miscalculated, except the universe did not calculate anything. We did. We measured, we calculated, We predicted, and our predictions do not match reality. This gap between prediction and reality is where science lives. This discomfort, this tension, this crisis. It is not a failure. It is an opportunity. The Hubble tension is calling us forward, demanding we think harder, observe more carefully, question more deeply. And when we answer that call, when we finally resolve the crisis, we will understand the cosmos in ways we cannot currently imagine. The calculation continues. The measurements improve. The crisis deepens. And somewhere, in some dataset not yet collected, some theory not yet proposed, some observation not yet made, the answer is waiting. The answer that will resolve the Hubble tension, explain the sigma-8 discrepancy, solve the lithium problem, all of it. The answer that will transform cosmology from a field in crisis to a field reborn. That answer is coming. The only question is when.